Good afternoon, ladies and gentlemen. Welcome to my talk. My name is Giovanni Meneghetti. I come from the University of Padua. Let me introduce also my co-author, Professor Mauro Ricotta and Bruno Azzoli from the same university. So, our talk is a contribution to the thermal methods to estimate the fatigue life in presence of notch effects. In this paper, we continued what we have done in previous paper by trying to estimate the fatigue life of notches characterized by notch tip radii lower than we have considered in the past. So the idea is to average the energy dissipated at the notch tip inside a properly defined structural volume. So the outline of my presentation is introduction and motivation. Then I will present briefly the experimental test program, and then I will present you the theoretical background concerning the two key points of the approach, that is the evaluation of the structural volume size and the evaluation of the heat energy dissipated at the notch tip. Then I will show you the experimental test results and I will draw some conclusions in the end. So, as you know, when you apply fatigue loadings to a notched component, at the critical point you have some energy consumption, so you provide some mechanical energy to the material, and some of this mechanical energy provided to the material is dissipated as heat, and some is stored by the material. In the literature, EP is the so-called stored energy of cold work. Now, of course, the probably more efficient idea would be to measure the stored energy of cold work, because it is responsible for fatigue damage and crack initiation. But we know that most of the mechanical energy expended in fatigue is dissipated as heat. So this energy balance looks like, say, 10 is the mechanical energy expended at the notch tip, 99 is dissipated as heat, and so the stored energy is only a small fraction. So if you try to experimentally measure the stored energy of cold work, the measurement will be affected by high uncertainties. So in the past, Kaleta and co-workers with Professor Harig in Germany tried to measure the stored energy of cold work. We all know that Hedin developed an approach based on the expended mechanical energy, but we tried to use the heat energy dissipated as heat to estimate the fatigue life. Of course, heat energy is only a manifestation of fatigue damage, is not by nature the fatigue damage itself, but it is a fatigue damage index. Now, if we look at a sharp notch, this is a typical infrared image at a crack tip, really in this case. The idea comes from Neuber's structural volume approach, where the fatigue damage index, in this case the heat energy, must be somehow averaged in a structural volume. So the fatigue damage index can be expressed like this. It is the averaged in the structural volume size, QC, and we have to integrate the energy dissipated inside QC. So we have two terms to define in this model: the size of the structural volume, RC, and we have to evaluate the average heat loss Q by means of this integral. So before showing you how to define the size of the structural volume and how to perform such integration, I would like to introduce the material we worked on in this paper. It is a hot rolled 4 mm thick stainless steel, low carbon steel. It had a tensile strength of 620 megapascal. We polished the surfaces in order to measure the energy dissipation with the infrared camera. The specimen's geometry is reported here. Here you see a plain specimen which was used to estimate the fatigue limit and find it experimentally. Here you see a sharply notched specimen we used to define the structural volume size. And here, with the radius of 0.5 millimeters, 1 and 3 millimeters, you see the specimens we used to test the approach. Fatigue tests were run in completely reversed loading, applying a load frequency between 5 and 37 Hz. The crack length was monitored by by means of a dim light digital microscope, and the thermal images were captured by means of a FLIR SG 7600 infrared camera. Thanks to an extended ring, we reached a geometrical resolution of about 1625 microns per pixel. Now, going back to the two main terms of the model, we have first to estimate the structural volume size. The idea was to use the proposal by Professor Lazzarin and Zambardi. They defined a structural volume size which has a slice shape at the notch tip, where the critical volume size is equal to this formula. The important terms are the threshold value of the long crack stress intensity factor and the material fatigue limit. You can recognize here the well-known Eladad, Smith and Topper length parameter, which is a material property, and here you have simply the Poisson coefficient. The small r0 parameter depends only on the geometry, the radius of the notch. Now, in order to estimate the Eladad, Smith and Topper length parameter, you need to perform a fatigue test on the smooth specimen in order to find the material fatigue limit, and you need also to perform fatigue test on very sharp notches in order to find the threshold value of the notch stress intensity factor. So you can see here the short staircase sequences we have adopted, where the fatigue limit resulted 404 megapascal, and here the short staircase sequence for the very sharp notch, where we found a threshold value of the stress intensity factor equal to 8.69 megapascal per square meter. From this value, you can calculate the Eladad-Smith-Topper length parameter and the RC value equal to 126 minus. Now, we have to evaluate the heat energy dissipated in the structural volume. So, imagine you take a picture with the infrared camera at the notch tip. We have defined the structural volume size. You have a number of pixels inside the structural volume. Imagine to define the mean temperature inside the structural volume. It has an evolution during a fatigue test. And at this point, imagine you suddenly stop the fatigue test. What happens is that the materials cools down, and if you take the thermal gradient measured just when you stop the fatigue test, you will obtain the average value of the dissipated energy. So you need just to know the material density, the material specific heat, the thermal gradient is measured when you stop the fatigue test, and you need to know the load test frequency. So let's go through these equations again, trying to imagine what we have seen in the laboratory. When you start the test, the mean temperature, T star inside the structural volume, tends to rise. When the heat production becomes equal to the heat, the thermal heat extraction from the structural volume, the temperature tends to stabilize. Now, suppose you start the infrared acquisition, you see the thermoelastic effect superimposed to the mean temperature level. If you stop the test right here, you measure the thermal gradient, the material cools down, and from this gradient inside this formula, you can estimate the energy dissipated in a unit volume of material per cycle at this point. So I would like to show you a short video. Yes, sir, please. You see here a video. We are in this case. You can see the thermoelastic effect superimposed to the mean temperature level. In a while, we should reach the point where the test is suddenly stopped and the material cools down. Yes, here we are. You can see the material which cools down, and if you measure the thermal gradient during this cooling phase, you can estimate here the energy dissipated as heat. Now, let's have a look at the experimental results. You can see here different examples of of cooling curves. You can see here an example from a smooth specimen. You can see here that the heat production was very high, so the thermal gradient is rather constant for a quite long time window, so the thermal gradient could be measured very easily. You can see, for example, for the case of a much sharper notch, the ranges of 0.5 millimeter, you can see that the time window useful to estimate the thermal gradient was much shorter. You see also that the thermal gradient was quite low in this case and was much higher in this case. So this is a typical experimental situation that can be seen when applying this approach. Now, if you plot the dissipated thermal energy in a unit volume of material per cycle, you can see that the thermal dissipation is quite constant in the case of plain material, but if you look at very sharp notch, the blue points, you can see that the thermal gradient has a typical value at the beginning of the test, and then it tends to be very low as soon as the crack starts from the notch tip. So the material cools down at the notch tip because the crack propagates farther from the crack tip. So you obtain typical curves like this. Now I would like to comment on the value of Q star, which is the energy dissipated inside this slice-shaped structural volume. If you compare the values of Q star, which is the mean thermal value inside the structural volume with the maximum value, you see that the two values are more or less equal. The maximum difference observed was about 10%. Now, in this case, for the present material and for the size of the structural volume of this material, the two values are very similar. So, in this case, the maximum value of the heat energy dissipated at the notch tip is more or less equal to the mean value. Now, I would like to present the summary of the experimental results in terms of energy. You can see here a plot of previous results we have published in the recent year. You can see here that we considered quite blunt notches with the ranges of 3 and 5 millimeters. Now, if we superimpose the results we have obtained in this case, where the notch radius was reduced up to 0.5 millimeters, you can see that they fall quite well in the same scatter band. But in order to appreciate this approach, I would like to show you the situation in the stress number of cycles to failure plane. You can see here the wall data, they are much scattered because the net section stress amplitude has been used here. You see here the red points, which are the results obtained in the present work, and again, if you see this situation in terms of energy, you can see that all data fall in the same scatter band. So, in order to conclude, fully reversed axial fatigue tests were performed on stainless steel in terms of specific heat loss averaged in the properly defined structural volume. Using the infrared camera, a spatial resolution of about 1625 micron per pixel was obtained, and we were able to analyze 3 notch ranges, namely 0.5, 1, and 3 millimeters. You see here the concept. We have a number of pixels inside the structural volume where we have averaged the energy dissipated, and you see the spatial resolution that we have obtained in these cases. And last, for the material and testing condition analyzed in the present paper, the heat energy measured at the notch tip was practically equal to that averaged inside the structural volume. So, this is the conclusion of my paper. My voice has also finished, so thank you for your kind attention.
If there are any questions, we can start the discussion. discussion?
I have several questions, but I'm going to start with the first one, a simple one. Could you go back to the slide 3, where you talk about the energy balance, the decomposition of the energy into stored energy and dissipated energy? Did you have the opportunity to estimate the ratio between the stored or the dissipated energy to the total energy in functions of number of cycles? Is there a change?
Sorry, I have interrupted.
No, it's okay.
That's okay.
It was my question.
We did not this in this work. We did in a previous paper. In the low cycle fatigue, you can actually measure very well the 3 different energy contributions, because the energy dissipated as heat is not very, let us say, it is on the same order that the mechanical energy and the stored energy. So you can easily distinguish and measure the 3 forms of energy. But in high cycle fatigue, most of the mechanical energy expended is dissipated as heat. So fatigue is a very, very dissipative phenomenon. This is our...
You have shown some results under mostly uniaxial loading, and when I turn to other kind of loading, to pure shear loading, what happens?
Okay. We did, not in this paper, but we did only few experimental tests in pure torsion loading, and what we found in a different material, not this one, it was an house temperature ductile iron in that case, is that in a very high cycle fatigue, the true energy fatigue curves between uniaxial and pure shear tends to coincide. Not the same in the low cycle fatigue.
Just a question to the cooling rate you determine. It's a main fact in your theory, but the cooling rate, I think, is influenced by the environmental conditions in the laboratory temperature and so on. Did you consider that?
Okay, so the point is this one. Let me go back to the energy balance. Here we are. So the concept is that the energy partition, when you expend some mechanical energy in fatigue of material, the energy partition between heat and stored energy is a material law. So the temperature reached by the material depends, of course, on the boundary condition. In August in the laboratory you reach higher temperature than in December, for example. But the heat energy you measure is always the same. This is the integral of the phenomenon. But locally, this energy balance is a material law. Of course, up to a given strain rate. We all know that if you increase very much the strain rate, this energy partition may change. So it is a material law depending on the strain rate. Okay, but in standard fatigue tests, 10 Hz, 20 Hz, this energy partition is a material law. And we did some, to complete the answer, we did some dedicated tests where we artificially varied the thermal boundary conditions, for example, blowing fresh air into the specimens or blowing hot air into the specimen and so on, and also varying the test frequency because if the test frequencies increases, of course the temperature increases, and you always measure the same thermal energy release, more specifically heat loss.
Only a curiosity, if you consider your analysis other shapes for the critical volume or only the silicon?
In this paper, yes. In this paper, we have considered we have considered the circular volume because in the school in Padua we have introduced this kind of shape or foregrounded notches. The shape is like this, but in principle you could measure the heat flow also by integrating the heat flow along the boundary. And so you could use any shape of the structural volume, for example, a half circle shape like Professor Taylor does, or maybe you could integrate the heat flow through the boundary in terms of reverse plastic zone size and so on. So you can apply this approach, whatever is the shape of the structural volume.
Yes, basically it's like critical distance that ends more or less.
The averaging idea of like critical distances.
Okay, if there are any questions?
Thanks.